Welcome everyone. So today we will see some of your advances for your final projects. Who would like to start? Yes, Amaury.
Can I share my screen?
I think so.
Okay. Okay. Can you see my screen?
Yes.
Okay. Give me a moment. Okay. Morning, everyone. My name is Amaury. I study physics, and today I'm going to show you my progress on my final project, which is about heterogeneity in random Boolean networks. So let's begin. And first of all, let's make a brief review, trying to remember my motivation. When we study complex systems, it seems that heterogeneity and criticality are very related concepts. In fact, we have reviewed this idea throughout the course. And in recent research, Dr. Gershenson and his colleague showed that the existence of a structural and temporal heterogeneity in a random Boolean network increases the criticality threshold. So the purpose of this final project is to introduce a third kind of heterogeneity, which we call functional heterogeneity. And this will boost the results obtained by Dr. Gershenson, showing that the heterogeneity extends criticality in complex systems, right? So, well, we need to clarify what heterogeneous functionality means. And as we saw a few classes ago, in a random Boolean network, the lookup table for each node has a bias of 1/2. What does this mean? It means that when we assign the lookup table values for a node in the initial configuration, there is a probability of 1/2 that the value is 1, and a probability of 1 minus 1/2, which is 1/2 2, that the value is 0. Okay, we call this notion functional homogeneity. Okay, and thus for this work, functional heterogeneity is synonymous with assigned a different bias, I mean a different probability, to the lookup table of each node, such that the average of these different probabilities is usually 1/2, right? How do we implement this in code? Well, Fernanda Sanchez-Puig is a colleague of Dr. Gershenson, and she has worked on a code to study random Boolean networks. With her permission, I made some modifications to her code in order to make functional heterogeneity possible to implement. What are you seeing on the screen is a function called configuration model. It's in her code and is used for assigning a spatial structure to the distribution of nodes in the network. Here, con is the matrix of connections in the random Boolean network, and bool is the lookup table of each node, right? And here in these lines, we observe the allocation of probabilities in the lookup table. Fernanda simply made the probability of having 1 equals to p, and the probability of having 0 equals to 1 minus p, okay, where p is usually 1/2. And in this next slide, we observe the modifications that I made right here on the underlined lines below. So first, I introduce a triangular distribution of probabilities. And then here, I assign one of those different probabilities to each node. And observe that the mean of the distribution is p. So if we make p equals 1/2, then the mean of the distribution will be 1/2, okay? With this adjustment, functional heterogeneity is already intrinsic to the construction of the network, and therefore we are done. Before moving on, please note that to generate the lookup tables, we use arrays of length 2 to the m, where m at most can be equal to n, okay? Where n is the number of nodes. And this will be important for the next slide, because now we can answer the question, what were the main difficulties so far? Well, the first time I ran the code, I used 100 nodes. Then after 9 hours of compilation, I received a memory error, which you can see on the left side of the screen. And similarly, I tried to run it with 13 nodes. And after running the first type of network, I again received a memory error, which you can see on the right side of the screen. And this is not only caused by the time it takes to execute, but also because the number of states grows exponentially as a power of 2, as we saw in the last slide. And then the memory fills up, which is the error I'm getting in both cases. Okay. In order to use an optimal amount of nodes, I decide to run the code with 25 nodes. And after 3 long days of compilation, I obtain the results that I will present in the following slide. Okay. So, well, this graph I present below is my preliminary result, and in it we can see the behavior of the average complexity with respect to connectivity. Since the criticality state is translated as the state of maximum complexity, if in the graph we observe an increase in the fall of the curve, that means that we're extending the criticality threshold, okay? All these simulations take into account functional heterogeneity, and the network types that I use are shown in on the right side of the screen, okay? Here, CRBN stands for a classical random Boolean network, which means that the time is homogeneous. On the other hand, DGARBN stands for a deterministic generalized asynchronous random Boolean network, which means that the time is heterogeneous. And in fact, for this last case, I'm using an out-degree dynamics, which means that the period of the random Boolean network is proportional to the outward edges that each node has. Moreover, the last term in these 4 vectors indicates what time of a spatial distribution the nodes have. Poisson refers to a spatial homogeneity, and exponential refers to a spatial heterogeneity, right? So in total, we have 4 cases. In all, there is functional heterogeneity. I mean, it's intrinsic, but in some, there may or may not be a spatial or temporal heterogeneity. Finally, here are the parameters that I use in the simulation, exceptuating the number of nodes, which I have to modify by the problem I mentioned before. All the other values were suggested by Fernanda. Okay, so finally, what's next? Well, if heterogeneity extends criticality, the result I hope to obtain is that when there is an overlap among the 3 types of heterogeneity, I mean spatial, temporal, and functional, the criticality threshold is maximized. And in fact, in this graph, the red curve is the overlap among the 3 kinds of heterogeneity. And as we can observe, there is a tendency to increase and never decrease as the other cases, okay? Okay, to prove this hypothesis, I have to reproduce Fernanda's results in order to compare functional homogeneity versus functional heterogeneity. And this is relatively straightforward. And in total, I will have 8 cases that I could present on a single graph to compare the critical thresholds among them. And of course, I'm going to work out on this during the vacation period. And then when we return, I will have the comparison among the 8 cases. And finally, I put here a series of possible extensions to my final project, okay? First, as we saw a few classes ago, free scale structure is very common in nature. And this is a clear example of a spatial heterogeneity. So maybe I could use this implementation that Fernanda already has made to study another kind of a spatial structure. Second, as I mentioned, I use a triangular distribution to generate the different probabilities in the lookup table of the random Boolean network. But of course, I could use other analogous distributions such as the normal, beta, and gamma distributions and try to find which extends more the criticality threshold. And last but not least, in 2019, Dr. Gershenson and his colleagues published a paper with the title "A Novel Anti-Fragility Measure Based on Satisfaction and Its Application to Random and Biological Boolean Networks." And in this work, they propose a simple calculable measure of anti-fragility, and also they found that the order random Boolean networks are the most anti-fragile. Therefore, I could study the relationship between anti-fragility and heterogeneity, and therefore the relationship between anti-fragility and criticality in these 8 cases that I mentioned before. And well, that's all for now. Thank you for listening. And if you have any questions or comments, well, I will be glad to answer them.
Yes, thank you, Mauri. These are encouraging results. I mean, it would be good to compare with the, like put them side to side to the ones that Fernanda had, because I mean, just out of memory, it seems to me that your curves seem broader, but they don't go so high, meaning that the, let's say the classical case of homogeneous everything would go all the way up to 1 for the complexity. Yeah, precisely that graph, around 3, and then would quickly go down. So what we were doing before to compare these different curves was to calculate the integral below the curve, but also for high values of complexity, in the sense that it seems that this type of heterogeneity does extend criticality, but in a way it limits the maximum criticality you could have. So that could be in some cases a disadvantage. But then it would be interesting to explore it systematically, and also, as you suggest, to compare the 8 cases and see how they affect each other. But another thing to do that you mentioned would be not only to compare with different distributions, let's say not only triangular or normal, but to vary the parameters of the distribution. So for example, now I suppose that your triangular distribution was from 0 to 1, but in principle you could make it narrower so that there is less heterogeneity. Still with a triangular distribution, the mean would be the same and the average would be the same 0.5, but then the variance would be reduced. And the same you can do with a Gaussian distribution. The mean would be 0.5, but then if the standard deviation is 0, then you have the homogeneous case. And when it tends to infinite, you would have a uniform distribution. So you could get another set of graphs just varying the sigma of the standard deviation of the Gaussian distribution and vary it from 0, which would be the homogeneous, to, let's say, a very large number that would be close to 1, or simply a uniform distribution. Basically, for each node, you select at random a value between 0 and 1, then the case in between. Because it would be interesting to see whether there is, let's say, a optimal heterogeneity that expands criticality more than others. And actually, the same could be done later for the other types of heterogeneity, whether you can explore the parameter space of different heterogeneities, and see which ones kind of expand it more, or whether there's a trade-off in the sense that the more you expand, the less maximum complexity you can get. But yet, that can be explored with what we have already. Also, for the structural heterogeneity, we were actually first considering scale-free distributions, but there was a problem because you would end up with, even with one or few nodes with lots of connections, and this would explode their lookup tables. And then, say, as you can see, you run out of memory quickly. So that's why we were using exponential. So that might be a limitation for exploring the scale-free distribution. And also, I don't remember whether I mentioned, because we were invited to submit an article to a special issue of Entropy Journal. And the deadline had passed, so we were not considering it anymore, but it was extended until September, so it would be a good venue to publish these results in a paper. And yeah, what you mentioned about anti-fragility is interesting. I haven't thought about exploring it, but it should be relatively simple to use the code that Fernanda and previously Omar Pineda have been developing, to use the same code to explore anti-fragility related to heterogeneity. So if we imagine the paper in different figures that would guide the storyline of the paper. A first figure could be just the functional heterogeneity, because in theory, we're finishing the paper with the other type of heterogeneity, so we should have submitted that one by then. So a first figure, just comparing the standard deviation of the functional heterogeneity. Then another figure comparing the types of heterogeneity. And then perhaps another figure related to anti-fragility. And I mean, we should have a meeting after the Easter holidays with the rest of the team to define this better. Yeah, has anyone else got comments for Amaury or questions?
Yes, publishing a paper sounds amazing. Of course, I'm interested, and I will try to implement these modifications that you mentioned and present them for the final presentation. I will send you my progress by mail. Thank you very much for the feedback.
Yep. Okay, if there are no comments, who would like to present next? You can also write in the chat and then have a parallel conversation in the chat. No importa.
Hi, everybody.
La cámara está. Si quieres, párate aquí.
I don't have a presentation, but my project is on random walks in random networks. And the main thing that I'm going to study is multiple walkers and finding out the encounter times of the multiple walkers. It turns out that if you have the master equation for a random walker, you could basically get an expression for these mean encounter times. So I'm doing right now a code to implement that equation and to see if there's a way to or to model this in different kinds of networks in a network that you can propose. Right now my code has an error, so I can't find it, and that's why I don't have preliminary results. But it's mostly there, and once I have this advancement, you could use different kinds of strategies for each walker and find out the encounter times, and for these walkers with different strategies. And that's basically it.
So if I remember properly, in previous works from Alejandro, they studied the average encounter times in different network topologies, right?
Yeah.
So what you would do would be do, let's say, different walks, but with different algorithms that would kind of give you different types of walks, or?
Yeah. The main first thing is to replicate the results from Alejandro Perez Riascos and David P. Sanders, and then it would be to use that code and give a different strategy to each walker. The main idea, the first idea is to compare a random walker and a random walker with stochastical resetting. That means that it would reset to a specific node with some probability and find out if that helps in some networks or doesn't help to make the encounter times, the mean encounter times, lower.
Yeah. Have you thought about other strategies?
That's the main one, but
Yeah,
we're open to other strategies.
Yeah, I could think like a simple one, which we could call greedy from the literature of search algorithms, that you stand on a node, and then from your neighbors you go to the best option with, let's say, almost deterministically, and only if there are two nodes that are equally good, then.
And the best one would be the most connected node, or?
Yeah, well, you can define
the best
different criteria to map those strategies, and I mean, probably if you do something like that, everyone would converge maybe to the best nodes, or and then from there they will go to the second best node, then they will go back. So then probably that would lead to very, let's say, relatively low encounter times, because then they would all go to the same.
Yeah. If we have an expression for the master equation, and we can work it to get the agent values and agent vectors, in principle, we could implement it into this. This thing.
And another strategy could be something inspired by ants, that let's say you could do something like that, but it's probabilistic, that you have probability of following a node proportional to the number of links that node has. But then you leave a pheromone trail, and then the probability of following a link would be proportional not only to the nodes, but to the pheromone.
Okay. Yeah, I'm gonna talk about it with Alejandro and see how we can implement that.
Yeah, or even without before the pheromones, let's say a simpler version would be very similar to the preferential attachment algorithm. So instead of attaching, you follow your neighbors proportional to the number of links that your neighbors have. So it will give you a similar dynamic of the rich get richer, and the extreme case would be, let's say, the greedy, where it always goes to the most connected node of your neighbors. And then the probabilistic version, which we could call preferential following. I don't know, because it's not attachment, but to follow preferentially the path towards the most connected node. That could give you some dynamics. And I don't know whether adding pheromones could overcome some of the peculiarities of certain topologies or certain connectivities, because if you have either very sparse networks or very highly connected networks, then you can have different probabilities of having local optima. So it should be greater in sparsely connected networks, that some agents would get stuck in a local minimum and not reaching. So that would mean that they would never encounter, some particles would never encounter.
Yeah, maybe the encounter times for those would tend to infinity. And
yep. And in principle, if you add the pheromones, then that should overcome that problem and take everyone to the global optimum.
Yeah, well, I'm currently working on it, but I can't find an error. But
yeah. So, I mean, I think I'm saying it's kind of adding time and probably there won't be enough this semester. Yeah. But it's just some ideas, and there might be some link between that and the literature of search, in the sense that if you find the average encounter times, then maybe that's related to the theory of how quickly you can find a solution for a specific network. I mean, there's a theorem that can translate any optimization problem to problem of traversing a graph. So that's why uncolony optimization can be used not only for traveling salesman problem and similar problems, but for any optimization problem. So you could do also the opposite, that what you are finding for networks and their navigability could be applied to all search problems.
Okay. Okay, sounds good.
Yeah. Anyone has questions? I didn't ask whether we are doing all presentations today or whether some will be on Thursday. It will depend on how many presentations and how long you take. It's like last time. Well, last time it was 2 days, but I don't know if we will have more or less presentations today, because maybe everyone thought, oh, I will present on Thursday. Yes, okay. Yes, you need to install the VIA app. Por favor. So, well, while we set up the presentation, someone else would like to have a go.
Hello. Yeah, I could present if you want.
Please go ahead, Anthony.
Yes, thank you. Hi everyone. So my project is on agent-based simulations of war. I'm not really interested on it for its military applications. I just think it's that combat provide a big variety of scenarios and problems to test distributed algorithms. But in particular, I'm interested in studying three main aspects of the armies: its movement, how information spreads, and its decision making. So movement is, inevitable. They need to move. Information spread. I'm thinking that armies. It would be interesting if armies didn't have full knowledge of everything in the battlefield at first. They should only know their main objectives, and as soldiers discover new features of terrain or enemies or whatever, they would have the option of communicating this to other agents so they could use it for their decision making. And decision making would be pretty much a list of objectives for each agent, which would have some weight or likelihood or urgency associated with it, and soldiers would use this weight to decide based on their surroundings and so on. But yeah, I've nailed down my main research topic, which I think it relates to these three aspects, which is the shape of the army or the structure of the chain of command. So there's three main possibilities I would like to model: one that is more distributed, one that is very rigid, and one that's kind of in between. So the first one is a horde or a swarm in which there is no chain of command. All agents are soldiers of the same rank, so movement we could implement something like a particle swarm optimization, which for those that haven't heard of that algorithm, it moves kind of like a flock of a swarm of bees or something very entropically. For communication, it will be distributed. All agents will communicate what they see to other agents.
We lost you.
Oh, sorry. Can you hear me now?
Yes. No,
sure.
No, I can hear.
Okay. Yeah. Well, to summarize, on the swarm model, everything will be pretty much distributed. And in contrast, I thought of the decentralized option is to have one leader who all agents communicate the information to, and he decides decides the behavior for all agents. And the in-between option is what is most used nowadays or in history, which is a chain of command or a pyramid or tree structure, where information moves up towards your immediate superior officers, and they can push orders down, but there's kind of different separate units or armies. So there's a centralized in locally, but distributed also. So yeah, but so I think it would be interesting to compare all of these three on fixed scenarios or with slight variations and see how well they do. One other thing that would be interesting to vary on these ones is the entropy. For all of these three aspects, I think we can, for instance, for movement, we could increase or decrease the entropy of the decisions. For communication, also how decided it is what they communicate. And decision making, also you could do the deterministic version where they always pick the best option, or an entropic version in which there's a probability associated, or you could have some sort of insubordination probability in which agents might not follow what's best. So yeah, that's pretty much the variables on the parameters that I want to explore. I would pick them first on a fixed environment against the fixed objects, the fixed objectives, and then against other armies to see how they compare. And well, the things that I would measure are the attrition rate, how much enemies are killed, how fast they reach their objective, and so on. But we could also measure the entropy, the information of the model, and such. So yeah, for implementation, I'm thinking I was trying to do something on NetLogo, and I've been playing around with some of the models from the library, but I'm thinking of using Python because it's more scalable. So yeah, that's why I haven't prepared a presentation. I changed my approach to for my final project. I will do it on Python. So that's pretty much my advances.
Good. I mean, of course, you could get different results depending on which kind of tests you perform. So it will be interesting to define what are you going to measure. I mean, in order to compare the different organizations, and what would be the task or goal, says whether it would be, I don't know, some exploration or some combat scenario, or I mean, what is the task? Because depending on the task and on the complexity of the task or the variety of the environment, then you can have say different organizations performing better or worse. I mean, one could be exploration, like I don't know, you need to find something, then you deploy, say, a battalion or a platoon, and then you kind of compare these different strategies where one tells everyone what to do, and another where everyone does, let's say, they make local decisions, and so on. So I think it would be interesting to use the ideas of Ashby of requisite variety to compare the performance of each organization, is that you could measure precisely with entropy the variety or the complexity of the environment or of the task, and also the variety or complexity of the organization. And probably if it's like a predefined static task, meaning that the variety of a single individual is enough to solve it, then that would be best. Let's say just to have a chieftain or let's say one big leader. However, as the problem becomes more dynamic, and it's in the extreme case, you would have like just random stuff changing constantly. They're very probably, well, that extreme would be like random strategy might be the best, or wouldn't be worse than others. So the more variety of the problem environment, probably the distributed swarm approach would be the best. And if you can explore these two extremes and several cases in between, then maybe the hierarchical case would be best somewhere in between. Yeah, I mean it's interesting. And of course you need to simplify in order to have results in the few time left.
Okay, sure. Thanks. Sounds good. Thanks for your feedback.
A bit less more. Well, just as a side note, I'm finishing, the book, the recent biography of Jean-Paul Neumann, who we could say that he created game theory, and it's interesting how it was used by the United States after the Second World War. So, we already mentioned that Jean-Paul Neumann participated in the Manhattan Project, but after the war, he kept his liaisons with the military, in general with the US government. So they were developing other types of bombs, hydrogen bombs, and also ballistic missiles, because once they had the bombs, they let's say already with the Cold War growing, there was the task, okay, where should we set up military bases so that we are better prepared with an eventual war with the Soviet Union. But it's not a trivial problem, because if you have several military bases with, say, with your nuclear bombs within firing distance of the Soviet Union, then they can destroy your bases quickly as well. So they favored like not to have bases close to the Soviet Union, but to have something which seemed more expensive but safer, which would be to send planes from United States and refuel them on air in case they would need to attack the Soviet targets. And at the end, this wasn't necessary because of development of rockets, and and also the reduction of the weight of the bombs, because before the atomic bombs and they were so heavy that they couldn't be carried by a rocket, and then they were reduced, and then they could be carried by rockets, and rockets were improved in such a way that then they could go, say, from almost anywhere and hit a target. I mentioned this because John-Paul Neumann in the 1928, he published a theory of games that later became very influential in economics. When he first published it, most economists didn't understand the mathematics, so kind of marinated itself until he again started working on it with several other people. And then in the 50s and 60s, it kind of started growing again. But after the war, the Air Force funded, started funding the RAND Corporation, which was a think tank where many people were using game theory to discuss scenarios for nuclear wars. So, for example, the well-known prisoner's dilemma arose from this research, and let's say initially they were thinking rationally, saying that a preemptive strike was the best strategy. Basically, we should try to destroy the Soviet weapons before they do that to us, because they will think the same and then they will attack us without any reason. But fortunately, they kind of developed the theory a bit more, and they use it precisely to convince decision makers that that nuclear war would most probably lead to a scenario of mutually assured destruction, also known as MAD. And basically, it doesn't matter who makes the preemptive strikes. It's terrible for both of them. So it's in the best interests of both United States and Soviet Union not to have a nuclear war. And very probably that helped prevent crisis like the Cuban Missile Crisis that didn't escalate. And nowadays we are kind of facing similar situation. Let's hope that decision makers don't forget the theoretical results of those years and make similar decisions. Yeah, because if you start deciding with your gut, you will end up making a wrong choice anyway. Lucrecia, did you manage to connect? Or?
Well, my project is going to be about algorithmic complexity and energy expenditure in the recognition and calculation of arithmetic operations in images. This is a very new topic for me, but I'm really interested and I want to learn about neural network and deep learning. So I read that imagine recognition is like the hello world of deep learning. So I get very interested. Well, so the problem starts with the recognition of big numbers. The characters are or give to the program in a special format. You could find the correct format for the number easily on Google, but it's a format called MMIST. But there is a big problem with the characters because they are not available in the correct format. So this is the first step of the investigation, creating the image, creating the set of arithmetic operation to train the deep network, and then obtain the interpretation. So I have learned now that the recognition of the character isn't the learning of the character isn't so difficult. But now I'm working on the creation of the image. And well, I have some problems because my characters are very, very ugly compared to the numbers. So, well, I will continue with the results I have and start with the learning process. Probably a lot of people here already know a lot about deep learning, but the main thing is that a deep network is a black box, so you can put a lot of nodes or neurons in hidden layers. So you don't really know what is happening inside the black box, but the thing is that all the weights that connect the nodes have an adaptation process that's called stochastic gradient. Well, these weights are adapted in a process, learning process. The important thing is that these neural networks they can extrapolate results. So the objective is that the program can give the result of an operation like this, but of a new image, not always the same, of course. This is just a sketch of how the image will be constructed. I first have the number. I have this character. Now I have to put all together. And well, because I don't have the training data, I'm thinking of creating it, like adding random numbers and random symbols, and create just a big set of operations with that training the network, and then hopefully it extrapolate new operations. So I have here some questions that I have, and of course some papers that I have found and help me to construct all of it. So the first question and the most important is how energy is measured in artificial neural networks. I have learned that I have to establish which is my level of study. Is it hardware or software? So I established that I have to study the energy in an instruction level analysis. That means that I have to study which part of the program is related to a specific task, and analysis the time and memory and the number of lines. Well, the second question, how much energy in joules does the program expand to predict and classify the 4 basic arithmetic operations? And to other questions that follow, and related to the energy and power. The third one does the time of running memory storage and number of instructions are useful features to study the algorithmic complexity in each of the 4 processes. With this question, I would like to know if there is a difference in these features when I'm studying different operations, or when randomly adding up operations come up in the program and spend less energy and less time than I see a difference. If there is no difference, so it's gonna be a result, but not what I'm hoping. The fourth one, how much time of running memory storage and number of instructions are needed to achieve the 4 process? This means to successfully have the result of the operation. And the fifth question, I know there are too many, but I like to have more. Which of the 4 processes are most likely to fail? Of course, I think it's going to be a division, but the result will. By now, I have done the neural network for the detection of symbols, which I already know. That was the detection of symbols was pretty much challenging. Now detection of numbers, the format. Before I have to test, now I have to make the test image and train a neural network. And I have not sure how am I going to find that for a learning vector. So that was I saw that vector in an article, but I think I can divide each of the detection of the numbers to and then I don't know if, of course, that's not sophisticated in a vector, but
Yeah.
I think
Yeah, I understand that you have 4 outputs because you codify the numbers in base 2, right? So then that will give you 16. And okay, yeah, what we discussed last week, whether the same network could be used for the symbols, because then you have 14 symbols. And I guess you can try.
yes, having 14 outputs.
Yep.
Yes.
And then you just apply the same network to each of the 3 parts of the input.
Yes, these are that's very common in neural network and training. And the loss is means where value and accuracy.
Yeah. It's recommended that your y-axis always starts in 0.
Okay.
So that you get a better idea on the differences, because otherwise these small differences seem big because we don't know how far they're from the origin.
Yeah. I thought that this difference was a problem in the code. But okay. Yes, so make them tiny codes because they are very well.
Yeah.
And it's such a recognizing number is not that difficult.
Well, from the training set, it might be that you just need more training because it starts improving and then it stops.
Yes.
So maybe just keep on training and people keep on getting better.
And here is just an example of a not predicted number. Can you see they are very ugly numbers, so the computer just confuse them. And of course, this will affect the final result of the operation. And well, the second problem I have is the energy measurement and algorithmic complexity. But it's not a problem. I don't have the idea. But I have learned that there are performance counters. So I'm learning about them and looking if they will help me to measure the participation of each part of the code.
Yeah.
And this is just a definition of instructional level analysis.
Yeah. I mean, once you have, so could you please go back to the previous slide? So the calculus of operations, those would be hardwired, or you would make another neural network? Or
I'm thinking of doing a simple
yeah, but not with a neural network, just interpreting the inputs and.
Yes, I'm thinking that the neural network outputs the numbers and the symbol. I know always that the symbol is the middle of the two numbers.
Yep.
First, I'm just going to abort the two numbers.
Yep.
And yes, just recognizing the two lateral numbers, the middle symbol, put them in the calculator and obtaining the result. But the calculator will have a different number of lines depending on the operation. Because there's no problem if there is an addition, add, subtraction. There is also different online code. But when we arrive to division, I have to add the not zero dividing, so that's one algorithm complexity more than the other. So yes, the last part is just our calculator and the energy measurement. I will put this counter when the whole thing is running and having result.
Yeah. But then if you use this calculator, I think that most of the processing would be for the recognition part, and then the difference whether it's addition or multiplication should be minimal, no?
Yes.
So maybe you wouldn't get difference of energy consumption or complexity because of the operations, because let's say you're not doing it with a neural network.
Yes. Yes, I thought in including another neural network to operation, but there exists for some rest and multiplication. There are, but for me are not easy to implement, but they are possible to implement. With division, there are just one neural network, and it's very difficult to implement. I'm thinking on adding just the addition and compare it. But well, I'm a little nervous about the last part. But if the energy measurement doesn't work, I think I will explore more about the recognition and the learning process. I thought maybe using other kinds of numbers, now that I have learned to change any image to, I can take any number I want in measure the same thing, but like rare and the complex, but the number of people like
Yep.
That was a plan B if nothing works. But
An option would be to apply energy measurement for the detection of numbers, symbols. And you could do two things: measure the energy while training, and then measure energy during the test,
yes.
the recognition.
Yes.
Yeah. And another thing is that, so for example, your neural networks might be recognizing characters and arithmetic operators properly, let's say with a high accuracy, but that doesn't mean that they are minimal in the sense that they could have lots of redundancy. So it might be that they're wasting energy in the sense that the amount of energy does not reflect the energy required by the task, but just that's the solution that the neural network found, and that is. But say one way of kind of going around it would be to have different measurements of different trainings. So you, I mean, you have a data set, and then you divide it in training and testing, and then you train, and then you test, and you get these results. But then you reshuffle your data set, and get a new training set. I mean, from the same data, but it will be different. And then you make the same measurements, and then you see whether it varies a lot. And if the standard deviation is low, then you say, well, might not be minimal, but we run it, I don't know, 10 times or whatever, and there was these differences. So then that could give you a bit more confidence in your result. Good. So someone else?
¿Cómo puedo hacer eso?
Envía, le pones dejar de compartir o algo así. So, someone else? Well, we have only about 10 minutes left. So, Odin, would you like to go ahead now or wait until Thursday?
Okay. Give me a minute to split all this. Sorry. I need to find my Zoom. Can you listen to me?
We can see you, yeah, and hear you.
Okay. So, and can you say something like a presentation?
Yes.
Okay, so I'm gonna be even faster. My problem is like all the code is falling down. Like I think another colleague has happened the same. So, well, the idea here is like we've been seeing on the course, like biological interaction can provide lots of complex and adaptative system. And with not going too deep into that, one of the nice ones are the mutualistic networks. We've seen something about the trophic networks or chains. But in this case, I had an abandoned project a long time ago, and I would like to recover. And I'm taking this advantage to do it. On the complicated plant pollinator mutualistic networks. Plant pollinators just represent any kind of network that the partners are different in the sense like the interactions are not the same between them than between the other partners, and this is called bipartite network. So the plants interact between them in a different way. They compete or they do whatever they want, and the pollinators also have different interaction between them. But the important for us is like the pollinators have a specific interaction to the plants. It's like they collaborate in, or they provide a service. The service is moving pollen between them. But there is a conflict in this interaction, being very, very short, right? The pollinators don't want to collect as much pollen or nectar or reward as they want. They are greedy interactors, and plants are also greedy, in the sense like they want the bees bringing more and more pollen from its same kind to them, and they don't want the bees to bring pollen from other kind of plants to them because it's a waste of time and a waste of resources. So basically, I've made a sort of game that is what I'm not managing to show you today, where it represents statically what is happening in, let's say, in one time frame, right? In that time frame, the every bee, let's say we have 3 species of plant and 2 species of animals, right? The animals allocate their visits to different plants, and the plants allocate its interest or handling coefficient to different pollinators. And just with those coefficients, we can create an interaction network, which, if any of you is familiar with the way of represent adjacency matrix in bipartite. So that will be, for example, the animals, and this will be the plants, right? And that will be the interaction between a little group of animals and plants, and another little group of animals, plants, and one plant and one animal. So, well, let me move back just in a second. In this mutualistic interaction, it might be cheaters, but we are not adding the cheaters at the moment to keep it simple. And there is a conflict between the spent energy and between the pollinators and the plants. We need to consider that the plants don't want to make too much nectar, and it was just to get pollen and get them fecundated, right? Okay, so the impossibility of showing you the game makes a bit random what I'm going to tell now. But if we think just in this kind of pollinators, there's a couple of researchers. One's called Fernanda Valdovinos and the other is Jordi Bascomte. They have done different types of differential equation modelings where they get to sort of different results. And the real life one also get like extra different results, right? But those kind of papers, particularly the one by Valdovinos and Marshland, talk about adaptative foraging, meaning like the animals and the plants adapt to themselves according to the circumstance, and they generate a kind of network that can be considered sort of modular. That is the one that we have here at the right. Bascomte's models and real life ones has found also this kind of interaction model called nested, which the big particularity is like the most generalist plants also contact with the most generalist animals, and the most specialist animals are dependent of the most generalist plant and the other way around. It's a bit tricky. So basically, the let's say, I don't know, a very specific animal will be in contact with those that are visited for most animals, right? This is contradiction with, for example, the very well-known the fig and the fig tree and the fig wasp, that they are one-to-one, right? And actually, in my model so far, I found two ways of doing it. I'm going in a second, and I found like those little modules happening all over the place. So the goal will be to try to find what is the optical dynamics and see how cooperation is maintained, what is the degree of generalist versus specialist and how they change over time, and particularly what is the network structure, if it is very modular or it is very nested according to the game I've generated. But the funny thing here is like we can imagine two regimes. One is like a community optimal, what is the best network structure and number of generalists and the cooperation, blah, 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 when the whole community is optimized. And I've done that using, well, I'm not very good in the math of and the algorithms of most of it. And so what I've done is a genetic algorithm that optimizes the network so the amount of reward of all the community is maximized. And in that case, I can tell you already, even with the mistakes, the modular setup is governing the dynamics. But when I try to get an individual Pareto optimal, which is again the same genetic algorithm, but now applied for in every time step, every plant try to offer their best solution to the situation, and the animals the same. All them get grouped together. It's called well-Russian economy, I think. It goes to the next step. There is a new situation, and it's get evolve, where rather than evolving the community, every animal and plant is trying to get maximize their benefits. And that's still where I haven't run, but I'm noticing already in the mock trials that with a little number of plants, now it's not modularity what we find. Similarly to the first person that presented today, having big nets, more than 10 by 10, it's a bit hardcore because I need, for the genetic algorithm, is not very efficient. So I need 1,000 chromosomes and many time steps, and it's very slow. So I was running last week for 4 or 5 days, one of those big networks, but with a mistake, I cannot say anything. So my plan for the next day is try to see what happened at a large community species, 100 by 100 or 10 by 10, but equal number of plants and equal number of animals, which is something many papers in simulation has been assumed, I suppose, for simplicity. And then when there is a huge imbalancement in the number of plants and animals, because this is what is going to generate forcefully non-modular networks or modules of different size at least. So, well, this is what I'm doing so far, and I'm sorry I haven't explained that clear as I would like. Well, if probably I'll be asking soon in the chats, in the forums we have, if anyone have like more experience than me with Python regarding networks, and also my abuse of genetic algorithm. But basically with the networks, I'm not able to plot so far those bipartite networks because I have either the animal bipartite or the plant bipartite. But actually this is in 2 cents. So it's weighted undirected in 2 cents, and I'm not being able to plot it. And with no plotting, it's very difficult to see. In the next presentation, I hope I can show how the game is set up, so anyone can contribute if anything more logical makes sense. But that's all. And I will ask for help if somebody can help me to change the genetic algorithm for reinforcement learning or min-max or something like that. I have in the brain how to do it, but my hands are not that fast like my imagination. Well, my hands, I mean, my programming skills are not that fast like my imagination. Thank you very much.
Yeah, thanks. Well, general advice is to start simulations with small sizes, in the sense that when you're starting a project, very probably you will change results sorry, you will change something in your code. So if it takes you, let's say, more than a few hours, then the advice would be to make systems smaller to get some preliminary results and just at least to get an idea whether you're going in the right direction, because more common that you will go in the wrong direction than in the right direction. So it's better to be able to change direction quickly rather than waiting for days and days and then something happens. And
Exactly. From previous run.
In the best cases, you can correct. In the worst case, you run out of memory and don't know what happened.
Yes. From old simulations of this kind with different model, really, like completely different model, it was a differential equation. But already I knew like it was a sort of critical threshold where interesting things start happening. But as you said, first it's better to try with similar kind of examples with 5 species each and like less number of parameters, and now eventually get it into the hundreds. And I mean, actually 100 is like a magic name in here. Don't know why. Yeah. Well, I suppose why. I hopefully in the next one it will be more interesting results with graphs plotted. Without seeing all the graphs, it's impossible. The most interesting thing of all this project specifically is like there is no way of creating a game or a simulation, simple equation simulation that is not hyper complex in the sense of you want to allocate visits and handling, but then you're affecting to the penalization of many plants being visited by many animals, and you don't want something like that. You also get like side effects all the time, and this is what makes the thing. Let one start thinking like has made a mistake, where maybe you have to accept sometimes like it's not going to be accurate at all.
Good. Also, if anyone needs a cluster, here at the C3 we have, so just send me an email and we'll get you an account. Yeah, but I mean, it's meant to be used. So if you need to use it, it's available. It is available, right? I mean, they were giving it maintenance some time ago. Oscar, el cluster sí está disponible, ¿verdad? El clúster del C3. Sí, sí. Yeah, I mean, they did some maintenance, but that was already some time ago. Okay, so see you on Thursday, and yeah, for the remaining presentations.